Hi everybody, today we're learning about piecewise functions. These are my favorite functions because I like to call them Mennonite functions. Get it? Because they're piecewise. Ha ha ha. Anyways, this is a website called coolmath.com. If you go to it and you search pre-calculus, you can scroll down and find the section on piecewise functions. You can see that there's actually a lot of great resources here at coolmath.com, so I'd encourage you to use it as a reference. So I'm actually going to go through, though, this description because I really like it, and then I'll formalize it with the note. So up until now, we've graphed things like, these different parabola, a line, an absolute value function, but now we're going to come into graphs that come in more than one chunk. So let's look at this one. So y equals, we do this curly bracket, x plus 2 when x is less than 1, and x minus 1 squared when x is greater than or equal to 1. Look, it's in two pieces. So each piece must only live in its own neighborhood. Let's put up a fence so we don't make any mistakes. So the fence is going to be at x equals 1. Okay, because that is the x value that separates this part of the function from this part of the function. So x plus 1 lives on the left side of the fence, and x minus 1 all squared lives on the right side of the fence. Now we just need to figure out who the fence owner is. So x plus 2 goes to the left. So he does not own the fence because x does not belong there at 1. This guy owns the fence because it includes 1 in his domain. So when we draw x plus 2 here, we're going to draw an open circle to show that he does not own the fence. But this guy does own the fence, so he gets a closed circle, and then you draw the rest of his equation, or his graph. Because he owns the fence. So there, that is the graph of a piecewise function. It comes in two pieces. So you can try that one. Okay, and you can continue and do more of this. All right, so you can check out that website. And piecewise functions can come in 3 pieces, or 4, or actually any number of pieces. Okay, so in this case, you would have 2 fences, one at 3, and that's the break between this function and this function. Okay, sorry, at -3. And then another one at 2, because that is the x value between this function and this function. So notice here that the green guy owns this fence, but the purple guy owns this fence. Okay, so he gets a closed dot because he's the fence owner. He does not own this fence, but he gets a closed dot here because he owns that fence. And this guy gets an open dot. Okay, so let's go through and actually do some examples. So in this note, we're going to actually define what a piecewise function is, create some equations, create some graphs given the equation, and determine if piecewise functions are actually continuous or not without having to graph them. Okay, we'll also evaluate functions, piecewise functions, using function notation. So here is, excuse me, a real life example. So a parking lot could charge as follows. So $5 for the first, $5 for the first hour, $12.50 for any time after an hour, up to and including 2 hours, and then $13 plus $3 an hour for any time past 2 hours. Now, why they would charge this way, who knows? But just humor me. So let's say this is hours, and this is the cost. So if I have even just 0.1 of an hour, I'm going to be paying $5, right? Even if I'm just there for half an hour, I'm still going to be paying $5. And for 1 hour, I'll be paying $5, right? Now, for any time over an hour, so like even 1.1, I'm going to be paying $12.50. Okay. And for 1.5, I'll be paying $12.50. And it says including 2 hours, so at 2 hours, I will be paying $12.50. But what happens after that? Well, any time past 2 hours, I will be paying this 13 bucks times $3 an hour. So for instance, at 3 hours, I'll be paying 16 bucks. At 4 hours, I'll be paying 13 plus anytime past 2 hours. So that's 2 hours. So it's extra 6 bucks. So I'm paying 19 bucks, etc. So what does the graph of this look like? Well, let's do 1, 2, 3, 4, and we'll do 5, 10, 15, 20. This is the cost, and this is the hours. Okay, so and this is 2, 4. So from 0 to 1 hour, I'm paying 5 bucks. So all the way up to 1 hour, I'm paying 5 bucks. So that's just a horizontal line. And at an hour, I'm still paying 5 bucks. So I'm going to put a closed dot there to say that at 1, I would go up to 5 bucks. But starting at just over 1 hour, I'm going to be all the way up here at $12.50. So right above 1 hour, directly above, I'm going to put the open circle at $12.50 to show that any time past there, I start at $12.50, but I don't at exactly 1 hour. And that's going to go all the way till 2 hours, where it's a closed dot because 2 hours is also $12.50, and that's going to be there. So what happens after that? Well, I know that at 3 hours, I'm at 16, which is about here. 4 hours, I'm at 19. At 2 hours, it would technically, if I was going by this rule, I need to have an open dot there. So it'd be 13 bucks plus $3 an hour for any time past 2 hours. So at 2 hours, there's no time past that. So I just have this little open dot at 13. And that should be a linear line there, right? Okay, let's just pretend there. Okay, and then that continues forever. Okay, so closed dot means, what did I say there? Including. And then open dot means not including. Now, it's important that you have an open dot and a closed dot, or else it wouldn't be a function. If you have 2 closed dots, that would make it fail the vertical line test. Okay, now how do we actually come up with an equation for this mess? Well, we want to represent the 3 parts. So we go f at x equals, and we're going to have 3 separate equations. So f at x equals 5 if h is between 0 and 1, and it includes 1. It's going to be $12.50 for h greater than 1, but less than or equal to 2. So that includes 2. That's why we have the closed dot. Now, this equation is a bit more confusing because it's 13 bucks plus 3 for all hours subtract 2, right? Because we don't include the first 2 hours. So we can just leave it like that. That's all h greater than 2. Or you can simplify this to be, you can expand and simplify if you want, or you can just leave it like that. I actually just prefer leaving it like that. And then we would identify our variables. Actually, we should go back. We don't want that to be f at x, do we? We want that to be cost at hours. So let c at h represent cost in dollars at h hours. Okay, so again, it's important that you understand closed dot goes with an equal sign, and open dot goes with there being no equal sign. Okay? So we must be careful on the fences since these are still functions. Only one neighbor owns the fence. So a piecewise function then is a function defined by 2 or more functions on 2 or more intervals. As a result, the graph is made up of pieces of similar or different functions. So if I give you a piecewise function like this, the first thing I do is deal with the fence. So the fence here is at 2, okay? So I want to first figure out which has a closed dot. So this is a closed dot here, right? Because it has the equal. So that's going to be a closed. What am I doing? Here. That'll be a closed dot. And this will be an open dot. Okay, so the first part is x squared. So if I put 2 into x squared, I get 4. So if I have x equals 2, and I put it into x squared, I get 4. So therefore, I'm going to have an open dot at 2, 4. Because that's where this function would end, okay? It goes right up to that point because it's for all x less than 2, but it doesn't actually get to that point. Okay, now for the second part, I'm going to put, if I have x equals 2, and I put it into 2x plus 3, I get out, 2 times 2 is 4, I get out 7. So I'm going to have a closed dot at 2, 7. Okay, so now on this side of the fence, I'm drawing the 2x plus 3, and on this side of the fence, I'm drawing the x squared. So if that's a point, I can find another point by just using my slope, which is 2, to find another point over 1 and up 1. Or I could just sub 3 into the equation. 2 times 3 is 6, 6 plus 3 is 9, and you'll see that that's the next point. Okay, and so that is that part of the function. And here, I just put in my values for x squared that I know exist. And I just continue that parabola. So there we go. That is the function that I was given, f at x. So it's x squared for all x is less than 2, and it's 2x plus 3 for all x is greater than or equal to 2. Okay, so you're going to need to pause the video and actually draw these. Okay, so this is all a 1-to-1 scale. That's important. So pause the video now and copy these down. Okay, so the first one, it looks like it comes in 3 pieces, but it's actually in 2 pieces. Okay, here, this is part of the function 1 over x. So even though there's a break in it, it's the same function. It just because it has a vertical asymptote there. So this is the function 1 over x for all x. Okay, so it stops at 2. So does it include 2? Yes. This has a closed dot, so it's going to include x equals 2. Now this is just the line x equals 3. And that occurs for all x's greater than 2, but not including 2 because that's the open dot. Okay, if I go over here, this is 3 sections. Okay, so section 1, 2, and 3. So my equation will have 3 pieces. So this piece here, it's a linear function. So I notice that its slope is minus x. And if it were to continue, it would go through a y-intercept of 0. So that's just the function negative x. And that occurs for all x's less than or equal to, because of the closed dot, negative 2. Now here, this looks like a parabola. And yeah, it goes through minus 2, 4, 1, minus 1, 1. Yeah, those points match up with the parabola x squared. And that occurs for all x values greater than negative 2, but not including because of the open dot. Now, here you'll notice that there's a closed dot that connects this function and this function. So really, you could have the inclusion with x squared or with this linear function. So I'm just going to include it with x squared. You don't have to. You can include it with the third piece, but not with both. Okay. So this one looks like it has a slope of minus 1 as well. And its y-intercept, if it continued, would have been here at 1, 2, 3, 4, 5, 6. So that's just minus x plus 6 for all x greater than 2. And there you have it. There is the equation of your function. So you just have to go through each piece, okay, and identify what the function is at each piece, and then make sure that you're putting the proper domain of that section, looking at closed dots and open dots appropriately. Okay, you can also be asked if a function is continuous. Okay, so continuous, remember, means that you could draw the entire function without having to lift your pen off the paper. So in this example, the examples that we just did, neither of these are continuous, okay? What makes them not continuous is these jumps, okay? So a linear function, a quadratic, and a linear, those are all continuous in and of themselves. So to check if the whole thing is continuous, you need to check at these joining points, so on the fences, to see whether you get the same y value. Because notice here, the function is continuous, even though you switch from one function to another, because they join at the same y value, this would actually still be a continuous function. But here, this messes everything up because they don't join at the same y value. This x value gives two different y values, which means you have to get your pen off the paper. But if this was at the same place, this would be one continuous function, even though it is piecewise. So, I mean, you can graph it and just look at it, or you can just check on the fences whether you get the same y value in either equation. So my first fence here is at x equals 0. So I need to check these two functions at x equals 0 if they get the same y value. Because if they do, then that means I don't actually have to lift my pen off the paper. So the first fence, okay, is x equals 0. So I'm going to put 0 plus 1. So I'm putting it into the first function. That gives me 1. And 2 times 0 plus 1 also gives me 1. So at that point, yes, it is continuous because they have the same y value. So now we need to check at the second fence. So these two, they have a fence of x equals 3. Do they have the same y value there? So this is the second fence at x equals 3. So 2 times 3 plus 1 is 7. And 4 minus 3 squared is 4 minus 9. Not looking good. Minus 5. Meh. It's not continuous. So even though it was continuous here, because it's not continuous here, there's a jump and you go from 7 down to minus 5. Altogether, the function, then we have to say that it is not a continuous function. Wah, wah. Okay, final thing. You just need to make sure that when you're evaluating for piecewise functions, you're putting the x value into the right piece. So for instance, f at minus 5, that you have to look at the fences. Is that less than -1 or greater than -1? Well, it's less than -1. So you go to this part of the function and you just say that it's -3. Now, f at -1, that is where the fence is. So do you go here or here? Well, you go where the inclusion is. So I need to go again with -3 because that includes -1, whereas this one doesn't. Okay, f at 0 though is above -1, so I'd put it into this function. So I'd get -0 squared plus 4, which is 4. Okay, so you just need to, when you're given function notation like this, you just need to say what is the x value in this section or this section, and then make sure you're plugging it into the right piece. So here's your success criteria for today. Make sure that you can do all these things as a result of this note. These are all the different types of things that I'm expecting you to be able to do after watching this video and practicing a whole bunch of questions and making sure you ask me lots of questions. So give it a read, and we'll talk about it more tomorrow. Thanks for watching. Hope you guys learned a lot.